Okay, so in our last class meeting, we talked at some length about the design project, gave you some outline suggestions on what should be submitted and how it should be combined together. So if you missed that discussion, I believe the video is posted on YouTube, so please review that. Maybe more immediately is homework 12, which you've got due in class on Monday. So like the entirety of what you need to submit for this class is homework 12 due on Monday, the design project on Friday, then there is a homework 13, which is due the last day of class, and then we have our final exam on Tuesday, May 6th. So 4 things. And the project, hopefully, you're mostly done with already. If you've done those draft submissions, then honestly, I think for the vast majority of you, that means that the project's 85% complete, maybe more. So we're definitely closing in on the end. I think we're at class 36 and we get to 43 if I'm not mistaken. So we're in the home stretch. Any questions about the announcements before we talk about water surface profiles? My office hours are so lonely and quiet. If you've got questions on the project, if there's anything that you can't figure out, stop by. Cheer me up. Come keep me company. Let's look at water gems together. Just let me know what I can do. I really want you to have something that you're proud of with this design project. I think that we don't have enough portfolio type things where we develop a work product that we could show somebody as an illustration of what we've learned, and maybe this is one of those. For a lot of you, I think you're on track to have something that you can really feel good about because the submissions have looked good. So we're going to talk about water surface profiles and then move into chapter 15 and begin an approach called the direct step method, which allows us to find depths when the flow is gradually varying. So you'll remember the process equation, which allows us to understand whether the water depth is increasing or decreasing in the direction of flow. So if the dy dl is a positive number, then that means that the water is getting deeper relative to the bottom of the channel. And if dy dl is negative, then that means that the water depth is getting shallower in the direction of flow. So the 3 depths that we care about when we're doing gradually varying flow is the normal depth, the critical depth, and for the location that we're at, what's the actual flow depth. So normal depth, of course, we would determine with Manning's equation, and that would be the depth if conditions were steady and uniform. But they're not, which is why we're talking about something else, because in gradually varying flow, there's some obstacle that is causing the flow to differ from the normal depth. Now remember, critical depth is the depth that's associated with a slope that would give you a Froude number of 1, because you can have a certain channel configuration, by which I mean the width and the side slopes and the roughness and so on. And if you put a certain flow rate through that channel, there's an infinite number of possible depths. If you have a really steep slope, then the depth would be shallow and the velocity is high. If the slope of the channel is relatively shallow, then you'd have a deep depth of flow. But the slope that is associated with a Froude number of 1, meaning critical conditions, we call that the critical slope, and that causes the critical depth. So we need to know the normal and the critical depth in order to assess things like whether the channel slope is mild or steep. And then also, if we compare y, the actual flow depth, to these 2 kind of theoretical flow depths, normal and critical, then that puts the flow condition into a certain zone category. That helps us to understand what the cause of the gradually varying flow might be. And it also helps us to understand how it's going to behave if we go upstream or downstream. Just comparing these 3 depths to each other can be diagnostic. So we're going to classify the water surface profile comparing these 3 depths, And it's useful to help us know what caused the gradually varying flow, and then also what's happening if we move away from the location of interest where we know the depth of flow. So the first piece of the puzzle is to classify the bed slope. A mild slope is one where the slope is less than the critical slope. And if we compare the normal depth and the critical depth, in a mild slope, the normal is bigger than the critical depth. So that's how you can know the slope is mild. If you have the characteristics of the channel, and you count, meaning like the width and the end value and the flow rate and so on, if you calculate and find that the normal depth is greater than the critical depth, then that tells you you have a mild slope. Whereas a steep slope, the reverse is true. The critical depth is greater than the normal depth. You already know this. We've talked about normal depth versus critical depth on several previous equations. There is the case that the slope could be exactly the critical slope. That sometimes happens, although not very often and for not very long. But it's possible that the critical depth and the normal depth are the same thing if you have a critical slope. And then there can be sections of a channel that are just horizontal, where there's no slope. If they're very long, then those just become lakes. But for a brief period, a channel could be horizontal, and in fact, a channel could even be adverse. You mainly see that at water parks. It wouldn't be in too many other locations that the water is going uphill. Maybe just a boulder. If there's a big boulder in the stream, then the water may go up over the boulder. And so for a brief moment, you could say that the slope of whatever it is under the water is adverse, meaning that the slope is uphill. So the main takeaway here is that what we do is compare the normal depth to the critical depth. And by the way, some figures are labeling the normal depth as y naught. Other equations or figures will label it as y sub n. The universe doesn't speak the same language in every location. We just have to adapt to it. Maybe use context clues to help us know what it means. So we're comparing normal to critical depth here. So the first way of classifying the water surface profile, and it's almost guaranteed you'll get a question on the exam where I ask you to classify the water surface profile. I don't want to make any guarantees just because I'm so forgetful. But, probably you'll have a water surface profile classification problem. And to classify whether it's an M, S, C, H, or A water surface profile, you first just compare the normal depth to the critical depth. So these letters M, C, S, H, and A just refer to what kind of a slope you've got. So like an M1 profile is on a mild slope. That's the first piece of the puzzle, is the letter that goes along with the profile. The next is which zone the actual observed flow depth is. So if we're at a location and we measure the water depth and it's deeper than both the normal and the critical, that puts us into zone 1. So the zones are divided by where these imaginary lines are. The imaginary lines are critical and normal. And so if we have a mild slope, we know that the critical is the lower of the two imaginary lines, and the normal is the upper of the two imaginary lines, and then the actual flow depth could potentially be in zone 1, zone 2, or zone 3. So zone 1 is above both the normal and the critical, zone 2 is between them, and zone 3 is below both of them. Now, which will be on top, the normal or the critical, varies depending on whether you've got a mild or a steep slope. Remember, a mild slope, the normal depth is above critical. A steep slope, critical depth is above normal depth. So an M1 means you've got a mild slope and the actual water depth that you're observing at that location is in zone 1, meaning that the observed, measured water depth is greater than either the normal or the critical. So I think you kind of get a sense of, you know, these combinations are the letters that we have, M, S, C, A, H, and then these 3 zones, although there are a handful of combinations that don't exist, and we'll go over that. So let's look at what it means in terms of dy dl. If you've got a positive dy dl, that means that the water depth is increasing in the direction of flow. dy dl is negative, that means that the water depth is getting lower. If dy dl is 0, then that means you've actually got uniform flow, meaning that the conditions may be steady and uniform, so maybe you could just go ahead and use Manning's equation. And then a dy dl that's negative infinity means that water's flowing over the edge of some cliff. So the main 2 we care about are these first 2, positive and negative. All right, so here's an M1 profile that's showing the shape of the water surface. So an M1 profile is getting deeper as you move downstream. An M2 profile is getting shallower as you move downstream. And an M3 profile is getting deeper as you move downstream. But an M3 profile means you've got a mild slope, but why would water be down here in zone 3 if the slope is mild? What could potentially cause the water to be that low? We saw it in the hydraulics lab. An underflow gate. Yeah, M3, it's what you'll see before the hydraulic jump occurs. So you've got a mild slope, but if the water is down here in zone 3, that means that you've got supercritical flow on a mild slope. So an M3 profile is on its way to a hydraulic jump. So we can know a lot by comparing the water depth to the critical depth to the normal depth. So here, why not? The normal depth is bigger than the critical. That's what makes these M's, is that we calculated both the normal and the critical, and normal was on top. So that means this is a mild slope. And then we also know, depending on where the actual observed water depth is, whether it's going to be getting deeper as you move downstream or shallower. So what would cause an M2 profile? It could be that downstream the slope gets steeper. And so there's some sort of a, not even necessarily a drop off, it's just maybe downstream the slope is steeper, and so you've got a certain water depth that's approaching a lower water depth. And M3 could be caused by an underflow gate. Here's a steep slope. And how do we know the slope is steep? It's because we compared the critical to the normal depth. Critical was on top. And so an S1 profile is getting deeper in the direction of flow. S2 is getting shallower in the direction of flow. S3 is increasing. So an S3 is not headed towards a hydraulic jump. It's just headed back towards the normal depth. There's not going to be a hydraulic jump if your slope is steep. But there could have been a hydraulic jump involved with an S1 curve upstream of the S1 curve. So there may be some sort of like an obstacle downstream of the S1 curve that's causing it, like a step. So there is no such thing as a C2. There's a C1 and a C3, but there's no C2, because if you've got the normal depth and the critical depth are the same thing, then there's no zone 2. Remember, if the slope is critical, then that means the normal depth and the critical depth are on top of each other. So that just means that there is no middle zone dividing zone 1 and zone 3. Similarly, for a horizontal slope, meaning a slope of 0, there is no zone 1, and there's also no zone 1 for adverse. So, you know, engineers prefer to understand things rather than memorizing things. But either way, you need to know all of these, whether it's flashcards or whether it's just having such a firm grasp on the underlying fundamentals that you could identify or recreate these sketches. You need to be able to identify and sketch water surface profiles like this. So let's look at some more water surface profiles and the physical things that could cause them out in the world. So if you had water flowing over a spillway, so this is like a reservoir behind the spillway. So you had normal depth that was approaching some obstacle that causes pooling. An M1 profile connects the normal depth to the spillway. So water is gradually getting deeper. We have a mild slope. An M2 was caused by water flowing over a drop. An M3 is downstream of a underflow gate, approaching a hydraulic jump, after which it settles back into the normal depth again. Those are some of the causes of those. And here in the steep slope, you can see an S1 would be caused by some obstacle downstream. When you've got a steep slope, is forcing the water to be in zone 1, above either the normal or the critical depth. So adverse, you could see an A3 if you had an underflow gate and the slope is actually getting, uphill. It could briefly occur as long as there's something afterward to allow the flow to continue, like a drop or a return to a negative slope. If there has to be enough momentum to carry the water over the brief period of an adverse slope. This is just another figure communicating the same stuff, whether it's getting deeper or shallower in the direction of flow, the comparison of normal depth and critical depth, and then whether it's zone 1, zone 2, and zone 3. So I think plenty of different figures to look and think and digest, and I won't talk you through them because I don't think that necessarily helps you with retention. What will help you with retention is just looking at this a couple of times and maybe trying to draw the sketches yourself. But we do need some practice classifying a water surface profile. So let's do this with a rectangular channel where we have 31 cubic meters per second going through the channel, which is 8.5 meters wide. So B, 8.5 meters wide. So from that, we're going to be able to calculate the critical depth pretty easily using the flow per unit width approach. For the normal depth, we will have to solve Manning's equation, the full version of the Manning's equation, because this channel is not wide. It's not wide from the technical standpoint, where you remember we say it's wide if it's 20 times wider than it is deep. This is not that. So to find the normal depth, we'll have to use the full version of Manning's equation. And then we'll compare y to yc to the measured depth of 3.2 meters. We want to know at the location where the depth is 3.2, what's the water surface profile there? So let me pause for a second and let's do that. Let's find normal depth, critical depth, and then see if we can figure out whether this is M1, M2, M3, or S1, S2, S3. I'll be writing some stuff on the whiteboard if you want to kind of keep an eye on that and confirm your own calculations. Okay, so Manning's equation will give us the normal depth. And if we substitute in Manning's equation, the flow rate's 31. It's a rectangular channel, so area is 8.5, which is the bottom width, multiplied by the normal depth. So that's A to the 5/3 power. Then we have slope to the 1/2 power, and then in the denominator, the n value of 0.033. And the wetted perimeter is the bottom width of 8.5 meters plus 2 times the depth. since we have the left side and the right side. So then that quantity, the wetted perimeter, is to the power of 2/3. So our only unknown in that equation is the depth. And if you put it into the solver, I think you should get 2.717 meters. I see some heads nodding, so that's always reassuring that you got the same depth as me. So that's the normal depth. And then the critical depth we need to know, because remember, classifying the water surface profile is you're comparing Y to YC to normal depth. Why not? So here the critical depth is, since it's rectangular, we can just say flow per unit width, lowercase q squared divided by g to the 1/3 power. So 1.107. So y sub c is the smallest, 1.107. And then is the normal depth, y naught, is 2.717. And then is the actual flow depth of 3.2. Is it 3.2? Yeah, 3.2. So if we go back to the figures, we have a situation where it's a mild slope because critical is less than normal. So that's a mild slope. And then the measured water depth is deeper than either of those two. So it puts us into zone 1. So this is M1 profile. This is an M1. And you need, when you're answering a question, whether it's homework or exam, you have to state what the criteria is that led you to that conclusion. And so you kind of have to show that you synthesized the pieces to come up with your answer, that it wasn't just a guess. M1 profile because YC is less than normal depth and Y is less than both of those other two. Let me show you what it looks like here. So the flow depth is greater than the normal depth. Normal depth is greater than critical depth. Thus, the water surface profile is M1. All right. So that gets us part of the way there. It's also asking to find the slope of the energy grade line, S sub F, so that we can calculate dy dx. Okay, S sub F we can find by rearranging Manning's equation for S. You can see over on the right-hand side of the classroom on that whiteboard, I've rearranged Manning's equation to solve for S. And what we do is we put in the, let me show you. We put in the actual flow depth of 3.2 as the Y. So we're substituting in the normal, the measured flow depth in both the area and the wetted perimeter to find the slope of the energy grade line. And then we also want to have the Froude number because we're putting it into the process equation. So S naught is given. We need to calculate the Froude number and the slope of the energy grade line in order to find dy dl. So let me pause for a second, give you a chance to write all this down for the slope of the energy grade line and the Froude number. Okay, so we've got the slope of the EGL. We've got Froude number. Remember, this formula for the Froude number is true regardless of the shape. So this formula works whether it's rectangular, trapezoidal, whatever. Froude number of less than 1 confirms that we've got subcritical flow at the location where the depth is 3.2. That's what we'd expect to see. Both of those we use to determine dy dl. So dy dl is the combination of the channel slope, the slope of the energy grade line, And then in the denominator, we account for the Froude number squared. And this is the dy dl being positive tells us whether the water is getting deeper or shallower as we go downstream. And this is positive. So that's what we would expect to see if we go back to the figures here that was saying, for example, a positive dy dl is associated with an M1 profile, where the M1 profile is where the measured depth is greater than either the normal or the critical. So everything's aligning as we'd expect to see a positive dy dl. But then the last piece of this example asks, compute, I guess that was all of it. But I do think it's interesting to find the slope of the water surface. So if we combine the dy dl along with the channel slope, the question is, relative to horizontal, we'd expect the water surface to still be negative. Otherwise, water wouldn't be flowing in that direction. So let me show you that, where the slope of the water surface is the combination of the channel slope and then dy dl, which is relative to the channel bottom. So if we want to know the slope of the water surface relative to horizontal, then we combine the channel slope. And here, remember, I've got the negative value for the channel slope when I am putting it here to find SW. So relative to horizontal, the water elevation is getting lower as you go downstream, even though the depth is increasing. So like, how does that work? What does that look like? Let's look at the figure again, because I think the figure that does a nice job illustrating that is this. Well, no, that doesn't actually do a good job illustrating it. This one does. Look at the M1 profile here. So the M1 profile, the water is still getting deeper in the direction of flow, but the water surface relative to horizontal, it's still, like, the water's flowing downhill. The water isn't, it's not getting deeper relative to horizontal. It's only getting deeper relative to the channel bottom. So any questions on this water surface profile example? Down here in the corner, I ask, what if the flow depth was 2 meters? So if the flow depth was 2 meters, then that would mean, that would put us between the normal depth and the critical depth. So that would put us in zone 2 if the measured flow depth was 2 meters, and then it would be an M2 profile instead of an M1 profile. So water can be measured directly at locations where there's a gauge. Gauges are very expensive to operate. Anybody have a guess of how many stream gauges there are in the state of West Virginia? I mean, like real stream gauges where somebody's maintaining them regularly, where the data is being consistently recorded. There are fewer than 300. And if you think about how many streams and rivers there are in the state, thousands, tens of thousands. If we're talking about creeks, maybe hundreds of thousands. It seems like every road in West Virginia has a creek that runs alongside it. And so we only have, a couple of hundred gauging stations in the state. And so a lot of rivers are completely ungauged. And for those rivers that do have a gauge, it's just at a single point. And so the Ohio River has lots of gauges, but they're spread out several miles apart. So even if we do physically measure the water depth at one location, then we may need to extrapolate from that location to understand what is the depth some distance upstream or downstream. So I think what I've got this linked to is the Ohio River at Huntington. Yeah, so this is what's been happening at the Ohio River over the last week. Water levels have come down by 12 feet. It was pretty rainy. There was some flooding previously. So we can in real time see what the water's doing in Huntington, but there's no gauge at, let's see, what's upstream a little bit? Lesage. There's no gauge at Lesage. So we need a tool that would allow us to extrapolate from where the depth is measured to some distance upstream or downstream. So the direct step method allows us to do that. This is a technique where what we can do is look at things like the critical depth, the normal depth, and go upstream step by step and find out how far apart is it to go from a depth that you know upstream to some other depth. So like if we knew, just going back to this gauge data, if we know that in Huntington the water depth right now is 28.67 feet. If I went 2 miles upstream, I could find out what is the depth unknown. Either I could go 2 miles upstream and find out what is the depth at that location, or I could say I want to go upstream and I want to find out how far is it to where the depth is 28 feet instead of 28.67. So the method that we're going to be talking about today, the direct step method, considers the difference in specific energy at two locations to estimate how far apart they are. And what it does is it calculates the conditions at the midpoint between two sections and extrapolates between them in the way that I illustrated with this figure in our prior class meeting. Like here, it'll look at the midpoint between two sections and it will assume that you have linear conditions between those 2 points. So this is kind of a visual representation of what we're going to be doing with the direct step method. It's limited in usefulness because the direct step method is going to assume that the channel is the same width between sections. And sometimes that's true, sometimes it's not. We have other methods we can use if the channel is getting wider or if it's changing shape. But that is an assumption based on the way that we're going to be applying it in the example today. So here's a summary of the method. We're going to use this energy comparison to find out at location 1 and location 2, basically where is the energy going. So we assume that at location 1 there's some water depth, y1. There's a water depth at location 2. There's a velocity head at both of those locations. But then the rest of the energy, here the delta z that exists at location 1, we can estimate that with the channel slope multiplied by the distance between point 1 and point 2. So that's dl. So if we're just trying to add up everything from the bottom of the datum to the top of the total energy line, there's delta z, the water depth, and the velocity head on the left. And on the right, there's the water depth, velocity head at 2, but then it's energy loss that accounts for this gap between the total energy line and the hydraulic energy grade line. So S sub F times dl, that accounts for the energy loss as the water's flowing down this surface that has some shear stress. Now we assume that the channel slope's not equal to the slope of the energy grade line. Otherwise we wouldn't be dealing with gradually varying flow. So it's a difference in energy between the 2 points that is accounted for by the differences in the depth and velocity head. So this is the specific energy. So E here is the specific energy. So if we move the specific energy to one side of the equation and then the difference in slopes to the other side of the equation, what we'll end up doing is estimating at the midpoint between upstream and downstream what is the slope of the energy grade line in between. And we do it that way because the energy grade line is curved, and we have to be cautious about how far over a distance we linearize it, but it's slightly less inaccurate if we find the slope of the energy grade line at the midpoint rather than at either of the ends. And then the distance between the 2 points is the change in specific energy divided by the channel slope minus the slope of the energy grade line at the midpoint. So we'll divide a long reach into several segments, each of which have a depth increase of 1/2 meter or less. And so I sent you a template file that I posted online. And we're going to go through it together to get a first taste of the direct step method. So we've got a rectangular concrete channel with a roughness of 0.02. It has a slope S0 of 0.0015. The channel is 7 meters wide and it's carrying 15 cubic meters per second. And then we measure the actual water depth at a certain location as 3.8 meters. So we've just been through an example where you calculated the critical depth, normal depth, and water surface profile. So let's just cut straight to the chase. Let me show you the solution for those here. Whoa. All right. So here's our example. The actual depth is 3.8. If we calculate the critical depth, it's 0.7. The normal depth is 1.195. So this is an M1 profile because the actual flow depth of 3.8 meters is greater than the normal, and the normal is greater than the critical. So the water is getting shallower upstream. It's getting deeper downstream. So we're going to find out if we go upstream, how far is it to the location where we get back to the normal depth. Here where it says, what is the length of the backwater curve? Another way of writing that is, how far upstream until we find the normal depth again? So here at the obstacle, we measure the depth as 3.8 meters. And one of the rules that we use here is that the depths can't be any more than 1/2 meter. We're going to find out how far upstream is it to where the depth is 1/2 meter or less. And we want to go upstream until we find the normal depth. So if you open up that template file that I posted, direct step 1, let's go through filling this in together. And we're going to have another example in class on Friday as well, so this won't be your only chance to try out the direct step method. Okay, so the width of the channel here is 7 meters. According to the problem statement, we're carrying 15 cubic meters per second. The channel slope is 0.0015, and then the roughness of the concrete is 0.02. All right, so you can see here that I've already indicated certain depths. So this is the depth where we know it's 3.8. That's Y7. And then what I've done here is I said, I know we want to go upstream until the depth's 1.195. So I just basically divided the change in elevation by the number of steps it would take to go upstream if we're limiting it to less than 1/2 meter. So that means we need to go in 7 steps. There should be 7 segments. And so we're going to calculate the area at the location where this is our flow depth. And so the area is, for the rectangular channel, the depth multiplied by the width of the channel. Anchor the reference there so that it'll always be looking up at this B value. And then copy and paste to all of these locations because we want to know what is the cross-sectional area of the channel at each of these locations where we know the depth. And so the velocity would just be Q, anchor the reference there, divided by the area. That's how we get the velocity. And copy and paste at all of these different depths until we get to the normal depth. So here at the normal depth, it's no longer gradually varying flow. If we go further upstream of there, it's just normal. Okay, E, the specific energy, is depth plus velocity head. So E is the depth plus V squared divided by 2G. So let me do V squared divided by 2 times 9.81. Okay. So now we've got the velocity head added to the depth, and that gives us the specific energy at each of the locations. So you can either drag it down. If you drag it down, then you're going to have to delete all of these locations in between. I'll show you in a minute why we've got this empty gap row. Actually, I'll show you right now. It's because we're calculating a delta E between them. Remember, we want to find out what's happening at the midpoint between where the depth is upstream 3.8 meters at one location and 3.366 at the other. So the delta E is the shallow one minus the deeper one. So that means that if you're moving upstream, there's less specific energy. Okay, and I want to find at the midpoint how much specific energy change is there as we're going upstream. Now, hydraulic radius is area divided by the wetted perimeter. I should have put in a column that had the wetted perimeter directly. I'll do that now. So here, P, the wetted perimeter, is going to be in units of meters as well. So the wetted perimeter is just the bottom width, anchor that reference, plus 2 times the depth. Since it's a rectangular channel, that gives us the wetted perimeter. Hydraulic radius will be easier for us to calculate now because we have hydraulic radius is area divided by wetted perimeter. All right. The slope of the energy grade line, we're going to have to wait. The suspense will be killing you, but it's 11:49, and I've kept you too long on a couple of recent occasions, and I just don't want to continue that trend. So save your work. When we get back together on Friday, we're going to continue this direct step method example just to refresh your remembrance here of the announcements. Homework 12 is due on Monday, and then Friday of next week is the design project. So I'll see you in class on Friday.